Hey guys, today we're going to be looking at a combustion analysis type problem. Now, combustion analysis is going to happen when you collect experimental data from a combustion reaction. Remember, a combustion reaction is the combination of a hydrocarbon with oxygen to produce carbon dioxide and water. What we're going to do is we're going to use experimental data from a reaction like this to work backwards using stoichiometry and percent composition in order to actually identify the species that is being combusted. We're going to do this starting with a practice problem. So let's go ahead and dive right in. All right, so let's attack our first combustion analysis problem. On the problem you see behind me, we have an unknown hydrocarbon reacting with oxygen to produce carbon dioxide and water. This is our kind of our stereotypical combustion reaction. Now, for the combustion analysis, we're given experimental data that 2.2 grams of carbon dioxide and 0.9 grams of water were collected as a result of this reaction. The first thing we need to do is to figure out how much carbon was produced in this reaction, because any carbon produced in this reaction must have originated from the hydrocarbon. And the reason is because in the reactants, that's the only location carbon exists. So we can go from grams of carbon dioxide produced to moles of carbon. So let's do that stoichiometry right now. Okay. So as a result of our conversion from grams of carbon dioxide to moles of carbon, we can see that there is 0.05 moles of carbon created from our original hydrocarbon. So that's how many moles were in our original hydrocarbon. We're going to do the same thing for the hydrogen, because if you look at water, the only place hydrogen came from, again, is the hydrocarbon. So we're going to do the same thing for the water. So in this case, we take the hydrogen in water and we figure out how many moles exist to figure out how many moles of hydrogen were in our original hydrocarbon. Let's do that with stoichiometry now. So you can see that we have 0.1 mole of hydrogen in the water. This means that our original hydrocarbon had 0.05 moles of carbon and 0.1 moles of hydrogen. To find the empirical formula, we're simply going to look at the ratio between these, divide by the smallest one. In this case, the smallest one is going to be our 0.05. We divide both by 0.05. And we can see our ratio is 1 mole of carbon to every 2 moles of hydrogen. Therefore, our empirical formula is CH2. So that's our first problem. Let's go ahead and take a look at a different type of problem next. All right, guys. So now let's do a very challenging practice problem. Part of the reason this problem is challenging is because of the fact that now, instead of just carbon and hydrogen, we're adding some other elements into our compound that is being combusted. This compound has carbon, hydrogen, oxygen, and nitrogen. And in our data that we're given, we're now given one other tidbit of information. We're given the amount of carbon present, or carbon dioxide present. We're given the amount of water collected, and we're also now given the percent composition by mass of nitrogen. What we're going to do is start this problem the same way we started the last one, which is by finding the moles of carbon and the moles of hydrogen in our unknown compound, because all of the carbon in our compound ends up in the carbon dioxide, and all the moles of hydrogen in our compound end up in the water. So the way we're going to start this is by writing out the amount of carbon dioxide that we have, 27.5 grams. We're then going to divide this by 44 grams of carbon dioxide per every 1 mole of carbon dioxide, multiply by the mole ratio of carbon dioxide to carbon of 1/1, and that's going to give us the total number of moles of carbon present, which is 0.625 moles of carbon present in our original sample. Once we've done this, we're now going to do it for hydrogen as well. Hydrogen, we're going to take the amount of water collected, the 9 grams of water collected. We're going to divide by the molar mass of water, which is 18 grams for every 1 mole, multiply by the mole ratio of hydrogen to water, which is 2 moles of hydrogen to every 1 mole of water, and we end up with 1 mole of hydrogen contained in our original compound. So now we know the amount of carbon and the amount of hydrogen in our original compound. We can find nitrogen using the 17.5% by mass, which means that we take the 20-gram sample that we had, multiply it by 0.175, or 17.5 divided by 100. Then what we're going to do is take that 3.5 grams that we end up with as a result, use that information to find the number of moles of nitrogen. So we divide by the molar mass of nitrogen, which is 14 grams per mole. And what we end up with in the end is that we have 0.25 moles of nitrogen present in the compound. So now we found the carbon, the hydrogen, and the nitrogen. What remains is the oxygen. And oxygen is very challenging here because of the fact that oxygen is not just in the compound, the original burned compound, but also in the gas that it combined with in the combustion reaction. Because remember, combustion is the combination of a hydrocarbon and oxygen gas. So we don't know how much of the oxygen came from the compound versus the gas, but what we do know is the mass of the compound that was burned, and from the number of moles of each of the other elements, we can actually figure out how many grams each of those elements made up. What remains is the oxygen. So let's do that math now. So what we're going to do is we're going to multiply the number of moles of carbon by 12, the molar mass of carbon, the number of moles of hydrogen by 1, the molar mass of hydrogen, the number of moles of nitrogen by 14, the number of the molar mass of nitrogen, and that's going to give us the number of grams of each. So now what we're going to do is we're going to take those masses we just calculated, 7.5 grams of carbon, 1 gram of hydrogen, 3.5 grams of nitrogen. We're going to subtract those from 20 to give us 8 grams. Now this is 8 grams of the sample that's unaccounted for, which means it must be the oxygen. 8 grams of oxygen, if we convert that into moles by dividing by the molar mass of oxygen, 16 grams per mole, means that we have half a mole of oxygen. Now we have all of the information we need to find the empirical formula of this compound, because we have the number of moles of each element within. So now what we're going to do is we're going to divide by the smallest number. The smallest number of moles that we have is that of nitrogen, which is 0.25. So we divide every single value by 0.25. As a result, we see that we end up with 2.5 moles of carbon. We end up with 4 moles of hydrogen. We end up with 1 mole of nitrogen. And we end up with 2 moles of oxygen. Now remember, because carbon has 2.5, we can't have an empirical formula with a decimal point. We need to multiply everything by 2. So what we end up with is our final empirical formula for the compound is going to be C5H8N2O4. All right, so now here's a problem that I want you to try on your own. Here we have a 7.2 gram sample that is containing carbon, hydrogen, and oxygen only. We have data that comes from the combustion analysis, which says that we collect 10.56 grams of carbon dioxide and 4.32 grams of water. The first thing I want you to do is to tell me how many grams of oxygen were in the original sample. Then I want you to tell me what the empirical formula of the sample is. And finally, going back to a video we watched earlier in the unit, I want you guys to take the empirical formula, and with the knowledge that we burned 0.04 moles of this sample, I want you to tell me what is the molecular formula for this unknown compound. So pause the video, take a few minutes to solve this problem. When you do solve it, or if you get stuck, unpause the video and I'll guide us through the answer. All right, so now that you've had a chance to try it on your own, let's work through it together. So in our original 7.2 gram sample, the first part of the problem asked to figure out how many grams of oxygen there were. Now the way we start this is we do stoichiometry to figure out how many grams of carbon and hydrogen there are based on the values of carbon dioxide and water collected through the combustion analysis. Now we know we collected 10.56 grams of carbon dioxide. So to convert to grams of carbon in that, what we're going to do is divide by the molar mass of carbon dioxide, 44 grams per mole. Multiply by the mole ratio of carbon and carbon dioxide, which is 1 to 1, and then multiply by 12 grams per mole of carbon to figure out that we have in this sample 2.88 grams of carbon. For the hydrogen, we're going to do the same thing we did with carbon, but we're going to do it with water, where we start with the fact that we had 4.32 grams of water collected, divide by the molar mass of water, 18 grams per mole, multiply by the mole ratio of hydrogen in water, which is 2 to 1, and then multiply by the molar mass of hydrogen, which is 1 gram per mole, giving us the fact that we have 0.484 grams of hydrogen. So here we know the amount of carbon, 2.88 grams, and the amount of hydrogen, 0.484 grams. And what remains out of that 7.2 gram sample is going to be the oxygen. This tells us that we have 3.86 grams of oxygen in our original sample. Now what we're going to do with that information is then convert all of those numbers back to moles in order to get to our empirical formula, which is the next part of the problem. So the next part of the problem asks us to find the empirical formula. We're going to take the number of grams of carbon that we found, divide it by 12. This means that we have 0.24 grams of carbon. We're then going to take the number of grams of hydrogen, divide by 1, which is the same number. 0.484 grams of hydrogen is 0.484 moles of hydrogen. Then we're going to take the number of grams of oxygen that we just calculated, the 3.86 grams of oxygen. We're dividing that by 16, and we get 0.240 moles of oxygen. Now these are our mole values, and with that what we can do is we can find the empirical formula by dividing by the smallest one. In this case, that is oxygen, 0.240. We divide each by 0.240, and what we end up with is that we have 1 mole of carbon, 2 moles of hydrogen, and 1 mole of oxygen. This means our empirical formula is CH2O. The next part of the problem said that if we have 0.04 moles burned, what is the molar mass? The molar mass of the molecular formula is going to be based off of the molar mass of the empirical formula, which is 30 grams per mole. We know it's 30 grams per mole because carbon weighs 12, there's 1 of those. Hydrogen weighs 2, there's 2 of those, and oxygen weighs 16, there's 1 of those. So the molar mass of our empirical formula is 30 grams per mole. Now, what we're going to do is we're going to find the molar mass of our molecular formula by knowing that out of 7.2 grams of our sample, that was 0.04 moles. So we're going to take 7.2 grams, divide by 0.04 moles. That's going to give us a value of 180 grams per mole. In order to go from our empirical formula to our molecular formula, you can see that we need to multiply by 6, which means we multiply our entire formula by 6, giving us a molecular formula of C6H12O6, which happens to be glucose. So here is the combustion analysis that resulted from the combustion of glucose. So that wraps up today's video. Today, just to recap, we looked at a combustion analysis type problem. We went through a few practice problems in order to really explore how we can utilize combustion analysis data in order to identify the species being combusted. I'd like to thank Noah Stone for his writing, editing, and filming of this video. Hope you guys learned a lot, and I'll see you in the next one.